Hello and welcome to Global Math Mentor. This lesson is about differential equations. What are differential equations? Simply speaking, an equation involving derivative. So you can see that this is the first order separable case. Why do you call it a first order differential equation? Simple. It has the first derivative. Unlike the second order differential equation where you will find higher derivatives, the double derivatives, or so on, right? So, okay, let's begin with this. What is the recipe of solving these differential equations? So my target is to find y in terms of x. So step one, how do you separate the variables? Keep dy here and move this differential of x, which is dx, to the right-hand side, okay? You can see the right-hand side has two kind of functions. There's a function of x and a function of y. G is a function of y, f is a function of x. So keep the function of x to the right-hand side because there we have dx. Move the function of y to the left-hand side because we have dy on the left-hand side. Stop and you can pause and think about it. What just happened? Okay, once you do this thing, second thing is integrating. Then we integrate the differential equation, and hence, by doing so, by applying the technique of integration, we eventually find y in terms of x, which is known as a general solution because there is a constant involved. You know, when you integrate, you put a constant of integration as well. So it looks a bit weird with the unknown. So I'm going to be solving some equations for you so you can have a better understanding how to solve a separable first order differential equation. Let's go. All right, let's begin with example one. I call this easy one. You'll see why. So you can see dy by dx is x times y. This is a differential equation because it is an equation and it has a derivative. Okay, so keep the dy to the left side and move the y, whatever you have related to y, move it to the dy side. So you can call this cross multiplication as well. Okay. Now dx to the right hand side and keep the x with the dx, right? This way, I have made this implicit form into a simple explicit form, which I can solve easily. Now integrate. So you can do this whole thing in a single step. I'll call this step is known as, for your notes, you can save it somewhere. This step is known as separating and integrating, right? So that's what we are doing. Let's integrate. So how do you integrate 1 over y dy? You can check your formula booklets, or if you haven't used your formula booklets, you just need to know that maybe you can, with practice, you'll be able to memorize that this is ln y. Sometimes they do write it like the absolute of y as well. The only reason is that the domain of log cannot be negative. So it's okay. If you want to put y or the absolute of y, it's fine. Okay, how do you integrate x? That is x squared divided by 2 and put a plus c. Well, this over here is known as, we call this the general solution. So why do you call it a general solution? It represents family of curves. It's not one specific function. So different c values will give you different values for the differential equation solution, right? But sometime in exam questions, they take you step further. They say make y the subject of formula, or sometimes they say write y in terms of x. How do you solve that? So if you have ln y, the natural log of y equals to x squared over 2 plus c, you know you can write it as exponential form, x squared over 2 plus c and equals to y. Well, that is your general solution, but y in terms of x. And there you have it. Are you wondering, how do you get this constant? That is another step in a differential equation. We call those things initial conditions or sometimes boundary conditions. What are initial conditions? Some x, y's are given to evaluate the constant. For example, I say example, you can add on a point 1, 0. Sorry, this doesn't lie on the curve. 1, 1, let's say, lie on the curve. So you can substitute 1 for y and 1 for x, and you can evaluate the constant. Okay, let's take a look at the next problem. I'm going to be solving this example too. I call this slightly harder. You'll find out why. Okay, let's do the same step. You can pause the video and try it on your own if you want to. All right, guys, let's take a look at this. dy. So by now, I think you know what's a separable case. And dx and x. I have separated the variables, now integrate, right? Okay, so what is the integration of 1 over 1 plus y squared? That is arctan y, right? So you can either write it arctan, or in some exam boards, you can write it tan inverse y. It's fine. Both are correct expressions. Okay, this will be x squared over 2 and plus c. Well, that is your general solution. If you want to write the solution like y in terms of x, what you can do, you can write y equals to tan x squared plus over 2 plus c. And that is your general solution y in terms of x. Again, no condition was given to evaluate the constant. Let's take a look at the next situation. All right, finally, apply initial condition. So what's the initial condition? What does this mean, y0 equals 2? This means that when x is 0, y is 2. Okay, let's solve this differential equation. So dy divided by y, and you can move 3 to the left or right, it doesn't matter, it's just a constant. So 3 dx. Okay, I've separated. Now I'm trying to integrate this. Ln y equals to 3x and plus c. So stop and think about it. By this lesson, like if you are studying differential equation, the prerequisite to differential equation is integration. So if you are weak in integration, make sure you practice and master the basic and slightly advanced integration skills before you move on to solve differential equations. Okay, now I'm going to evaluate finally my constant. Okay, so if I substitute y2, ln2 equals to 0 plus c. So I encourage that do not write the decimal values for the constant. Keep them as exact as possible. You'll see like why. The solutions look very nice, and later on in higher exam problems, they ask you to identify like what happens to y as x tends to infinity, or what happens to x as y becomes very large or small. So to answer questions like these, exact forms are better. Exact form. Keep that in mind. Take notes if you are writing it somewhere. Okay, so finally, my solution will look like 3x plus the natural log of 2. Uh, Students, please do write this. This is known as a particular solution. Okay, this one was the general solution. Why do you call this the general solution? Because the constant was not evaluated, but this time the constant is evaluated. Okay, let's try and write y in terms of x. So what do we do? You might be thinking like, my lesson is about solving differential equation, but why am I encouraging you to write y in terms of x? But because that's what most of the exam problems are like. So ln y minus ln 2 equals to 3x. You know that when logs difference become a quotient, right? So you can write it like this. And finally, e to the power 3x will be y over 2. And this implies that y will be 2e3x. So this was actually the curve, which was sort of written as that differential equation. This is the general solution, y in terms of x, right? Okay, so in the last part of the video, I'll solve an actual exam problem. So this is, again, a separable first order differential equation. My differential equation looks like dy over dx equals to x. Now, look at this. This doesn't seem a separable case at first because e has a power x plus y, but I can write it as ex and times ey. You see, what did I just do? I am reversing indices. So you can break this back. So think about it, like if I, again, since the bases are same, you can add the powers, so it will look like e to the power x plus y. Now let's quickly separate this dy over ey, integrate, and ex dx, right? Okay, so e to the power negative y, and we have dy equals to ex dx. Can you guess which case is this? This is a by parts integration case. So you can practically face any sort of integration while you're solving differential equations. So that's why I was saying that integration comes first, and then when you master integration, you can start solving differential equations. So e to the power negative y divide negative 1, because when we integrate exponentials, we divide by the power's derivative. And this, I can show you the breakup. Like, so u will be x, and dv will be e to the power x, du is going to be dx, and v is going to be ex, right? So I need these four things. What's the by parts integration formula? It looks like u dv equals to uv minus v du, right? So I'll make a separate video on that. So I hope you know how to integrate by parts. So this will look like xex minus integral v, which is e to the power x, and du is just a dx. Now I can finally write xe to the power of x minus ex, and minus e to the power negative y. And there's a plus c as well. Let's try and solve the constant of integration. So I've got the boundary condition of y equals to 0 when x equals to 0. So let's sub in. Minus 1 equals to 0 minus 1 plus c. Any number raised to power 0 is 1. This cancels. C is 0. So my general solution, particular solution will look like minus e to the power minus y equals to xex minus ex. I need to write y in terms of x. So let's get rid of this negative first. It will be ex minus xex. Apply logarithm on both sides. So minus y will look like natural log of ex minus x e to the power of x. Okay? Or last, you can write y equals to minus ln e to the power x minus x ex. That is the answer to the first part. So there are different ways. Any equivalent form is acceptable. Let's take a look at the next part. So this is what I was talking about. They can sometime add on some extra parts and ask you, like, explain why x can only take values that are less than 1. So how do you answer that? Look at your general solution. It's a natural log. You know that log's domain is always positive. So ex minus x, e to the power x should be greater than 0. If you factorize the ex out, it's going to look like 1 minus x greater than 0. Now, ex is always greater than 0. That's understood. But when you solve this linear inequality 1 minus x greater than 0, you will see that x is less than 1. Hence, it's proved that x can only take values which are less than 1. Or you can say indirectly, because any negative value for x will make the domain of logarithm positive, right? So this was the separable differential equation case. This was the linear case, and stay tuned for more videos, and I'll explain the later types as well. Over and out.